everyone, it's Professor Stevens. I'm here to rescue you. I'm going to do one of these problems for you that you might have been a little thrown off by because you haven't seen this sort of thing in a while, since chapter 3 to be exact. So when you have problems in section 7.2, which have raw data instead of summary statistics, you can either open it straight into Excel, or you can copy it to a clipboard and put it into an already open Excel spreadsheet, which is what I'm going to do. Right click and copy, paste. That didn't work very well. That's not what I wanted. There we go, that's what I wanted. All right, so now that we've got that, we can do this sort of problem the exact same way we've done every other construct a confidence interval type of problem, as long as we have the sample mean and the sample standard deviation, and the sample size, of course, and the confidence level, of course. And since we were given the raw data this time, we will do the step of finding the summary statistics, ourselves. So I'm going to just make a little room here on the side. Not that it matters where it goes, but I want to come down here to the bottom of my stuff, and I'm actually going to freeze that so that it's easier to see. Okay. All right, so down here at the bottom, I'm going to come up with my mean, my sample standard deviation, which I guess I'll use the symbol names X bar, which is usually the X with the bar on top of it, and S for the sample standard deviation. So we learned how to do this by finding the sum, adding up all the values and dividing by n when we were in chapter 3. We also learned how to use the average function built into Excel already as a way of checking our answer. And since I'm not testing you on your ability to find the average using a formula, like a mathematical formula, you can use the Excel function for this step. So I'm using my average function and then selecting all of the males' data values. Let me go over here real quick and just introduce the problem a little bit better so that at least we have some sort of context here. It says refer to the accompanying data set and construct a 90% confidence interval estimate of the mean pulse rate of adult females. Then do the same for adult males and compare the results. So for this problem, that's what's been given to us, is two sets of pulse rates, one for males and one for females. We're going to construct two confidence intervals, one for males, one for females, and then we're going to compare them to see if there's a significant difference between the pulse rates of males and females on average. So now I have my average pulse rate calculated here, and remember the round-off rule for measures of center and measures of variation, which are things like the mean and the standard deviation. The round-off rule we learned in chapter 3 was one place more than is present in the original data values. So as you can see, all my male pulse rates have no places shown after the decimal, which means that I'm going to round my sample statistics, my measure of center, my mean, and my measure of variation, my standard deviation, which I haven't calculated yet. I'm going to be rounding those to one decimal place because that's one more than what the original data shows. Now, I can go ahead and do the same thing. Well, not the same thing, but I'm going to put an equal sign and use S. I start typing in standard And I only got the S and the T in there. You can see down here, standard deviation for the population. That's what that P on the end means, dot P. Standard deviation for the sample. That's what we want here. So we'll go ahead and select all our X values again. And so now I have my two sample statistics, which will be needed to construct my confidence interval for the male pulse rates. And I can drag those formulas over. So now I have the second set for my males and my females. And I'm ready to start calculating the E for each of those sets. So I'm going to first need a few other things. I'm going to do the shorthand version of this. Well, should I? I guess I'll walk through the whole thing. So I'm going to need my confidence level, which leads to my alpha or my significance level. That's alpha. I'm going to need my alpha half, which is my significance level half. And actually, to be honest, I don't need all that when I'm using technology. I'm going to simplify this a little bit. I don't want to do the whole spiel because I'm more focused on really all I wanted to show you. I've shown you already. I wanted to show you how to find these so that you can get the rest. Use those in the formulas for E and for the confidence interval limits. So I'm going to take a few shortcuts here and showing you the remaining parts. So I'm going to do the critical value, which is, for this case, it'll be a t-score because I'm dealing with sample data. And then from that sample data, I found my sample standard deviation. I don't know what the true population standard deviation is, so my critical value is going to be a t-score. And I'm going to find that using the t-inverse two-tailed with an alpha of, well, the confidence level is over here. You can see 90% confidence, which makes my significance level, or my alpha, will be 0.1 or 10%. And since this function is built to be two-tailed, you can see it says dot 2t, which means two-tailed. I will put the entire alpha in there, and the function will do the dividing in half for me. And then next, you can see down here, after the probability, it wants the degrees of freedom, which is n minus 1. So to know what n minus 1 is, I would have to count all the values, or possibly it could have been given in the problem. Let's see, it says refer to the accompanying data set. Now it doesn't say any. Sometimes in this setup, it'll say the number of values in the sample, but it doesn't for this one, so we're going to count them. And you can see how my labels start in row 1, and my last data value is in row 41, which means I have 40 values. Yeah, exactly, 40 values. So I now can put after that comma, the 40 minus 1 is 39 degrees of freedom. And I can actually copy that over too for the females. And then I can use that to calculate my E, which is equal to the critical value times the standard deviation divided by the square root of n. That's the critical value times the standard error. And I will be doing the same thing again right here. Okay, so there's my margin of error. And I can start constructing my confidence interval limit for my females and my males. And I will do it like this. I will say, here's my confidence interval limits, and I'm going to do lower and upper limits, or left and right limits. So for the males, I'm going to use my equal sign first, and I need to start with the point estimate, which is the mean, the sample mean, so that's x bar. And then I'm going to stretch the net from my point estimate. I'll subtract a margin of error for my lower limit, so I stretched it lower, and then I will stretch my point estimate up by that same margin of error. So now I have an interval that starts at 63.5 beats per minute up to 70.1 beats per minute. So with 90% confidence, we think that the mean, the true pulse rate of males will fall within that region. For the females, you might have guessed that I can drag that over once again, and I have all my answers there. So that's how you handle a problem like this one. You know, on first glance, you might open it up and panic because there's so much data and because you have to do not one, but two confidence intervals. But it's really not all that bad, is it? No. With Excel, it's not a big deal, right? Because you don't even have to, it used to be with using the graphing calculators, you would have to type all of that in to your lists in the calculator to do this problem. With Excel, being able to just copy and paste, it's so quick and easy. So, and also with these nice little formulas, it's very nice. No big deal, guys. Just do it. Now, we would give the answers. It tells us to round to one decimal place, although we should know that because that is the round off rule. Because the round off rule for confidence intervals for means is to go, if you were given the raw data, you go one place more, just like when you do your summary statistics. And if you were given summary statistics already rounded, then you rounded the same number of places in your final answer for your confidence interval limit. So we're good with our rounding already. So we'll go ahead and put this in here, 63.5. And then we're doing the female. Oh, I'm starting with the males. I should be putting in, it says construct the mean pulse rate for adult females. So they want the females first here. So let me back that up. That should be 72.8 and 79.7. Alright, and then for the males, 63.5 and 72, whoops, I'm looking at the wrong number, 70.1. And we'll check that answer. Nice. And now the comparison. Well, even before I read my choices, I'm just going to look at what we have here. I have 63.5 and 70.1. So what is that? 63.5 to 70.1, right? I don't even know what I'm trying to do here exactly. And then 72.8, that's going to be somewhere above that last one, right? 72.8. And then up to 79.7. So what I'm trying to show is that on an actual number line, $79.7. On an actual number line, you can see that the males seem to have a lower interval than the females do, right? You can see that, right? Okay, so let me just try to type this in for visualization purposes. All right, so just trying to picture a number line. 63.5 is the lowest, and the males go up to 70.1, and the females start above that at 72.8 and up to 79.7. Now, what we're looking for here is whether or not they overlap. Because if there's overlap, then some of their pulse rate averages are shared. And so, or I should say, the average estimate net is containing some of the same values in each interval for the males and the females. So then you could say, well, there's not a significant difference because there's overlap and they have some of the same values inside their estimates. So here we don't have overlap, which means that they are significantly different. So we will say that since there's not overlap, there is a significant difference according to this sample at least. According to this sample and these methods, we've found that there's an indication here, there's some evidence to support the idea that possibly men and women have different, significantly different pulse rates. Okay, so let's see which one is it. They all start the same. The confidence intervals do not overlap, right? That's correct for us, so it could be A. The second one says the confidence intervals overlap. That's wrong, so it's definitely not B. C says the confidence intervals do not overlap. Okay, so C could be our correct answer. So A and C are two that could be our answer. The confidence intervals overlap. No. Okay, so it's definitely going to be either A or C. And then it says, so it appears that adult females have a significantly higher mean pulse rate than adult males. All right, so let's look at that again. Let's look at the little visual here. Does that seem right? Females seem to have a significantly higher average pulse rate than males. That's what it looks like because the female's estimate interval estimate of the pulse rate is average pulse rate is up here, fully above the male interval. All right, so that looks good. Let's just read that other one to be doubly sure we've got the best answer, because I think it is A. So let me just check on C again. The confidence intervals do not overlap, so it appears that there is no significant difference. No, that's the opposite of what we think, right? Because there's no overlap, they're not sharing any estimated averages. So yeah, there is a significant difference. This doesn't make sense. So then A is the best answer. Let's check it out. Yeah. So that's how you handle that kind of problem. Not a big deal, right? I also was going to write out this calculation on here for those of us who feel a little freaked out by watching the spreadsheet business. Remember the E formula, well, actually I could start a little bit further than that. Remember that a confidence interval is always the point estimate, which is the sample statistic. In this case, since we're doing averages, it'll be the sample statistic x bar plus and minus the margin of error. Because the whole point is that we're taking a point estimate. It's really hard to draw with a mouse. We're trying to take a point estimate and stretch it out to an interval to try to catch the true mean. We're trying to estimate. The confidence interval is supposed to be an interval estimate. I don't know why I'm writing all this out because I could be typing it. Some things I need to be able to draw, but this I do not need. I do not need to write out estimate with my mouse. But I'm going to keep doing it because I already started. Estimate mu. like that. Okay, so the true population mean mu, we're taking an interval estimate, a confidence interval estimate, and we are taking our point estimate, which is X bar, and stretching the net up and down by a margin, or right and left, bigger and lower, higher and lower, by a margin of ARV. Okay, so that's going to be how we get our interval limit. And so let's figure out how to find E, because we already did the step of finding. Let's do just the one for males. Remember the, oops, I went too far. The males X bar is 66.8, right? So just doing the one for the males, X bar right here is 66.8. Gosh, so hard to write with this thing. Why don't you just type? I don't know. 66.8 plus and minus rather, E. Now we need E. We got to calculate E. Remember, E is always the critical value, which is either going to be a t-score if you don't know the true standard deviation from the population, which is usually the case in real life. We don't usually know what it is. That's supposed to be a star or an asterisk to indicate multiplication. And then times the, what is it? Oh yeah, the standard error. Standard error, which is the sample standard deviation divided by the square root of n. That's using the central limit theorem. So we have our t-score, which we could find using the table or with our t-inverse. And we got 1 point. Actually, let me use the table on this step since you guys probably are wondering how to do it with the table too. And it's going to take me a minute to get there. It's buried way down deep in my files. Where is it? There it is. Okay, so my t-score table with the degrees of freedom of 49, the closest degrees of freedom is 50. We've already done so many examples where it was 50 that we had to use from the table. It's strange. In fact, I think every example we've done so far this semester has been 50 degrees of freedom from the table. All right, so it's the closest we've got, so that's what we're going to go with. We just have to line it up. We have to make sure we get the right column. So with 50 degrees of freedom, we know we'll be in that row. And which column we will be in? Well, it was a 90% confidence interval, which means you have an area of 0.1 or 10% total in both tails, and in each tail divided up evenly 0.05. So this is the correct column. This is the fourth column from the left. So I'll line that up with my 50 row here. So that the value is 1.676, which is pretty close to what I calculated right here. Whoops, what happened? Yeah, see, it's different. It's more accurate in the Excel spreadsheet since we can use the exact degrees of freedom. And also because everything in this table is also rounded when it's written down, rounded to 3 decimal places. So 1.676 we can put down here as our critical value from the t-table. 1.6. Why aren't you typing? I don't know. Oh my gosh. I'm going to go ahead and type. I can't take it anymore. It's too bad. 1.678, right? And then times the sample standard deviation, which was over here, 12.5. Gosh, things are moving a lot faster with me typing. And then the square root of n, which is one of those places that I feel like I want to write, divided by the square root of n, right? Which is, what was n again? 40. Let's go ahead and do that. 40. All right. And so let me use my calculator over here. I'm going to use Excel as a calculator and see if I get the same result as I got in this step. I'm just going to move this over a little bit because now I'm doing the males again. I want to do the males again using the table and see if I get the same result. So I got, for E, I got 1 point, I gotta put the equal sign, 1.678 times 12.5 divided by the square root of 40. Oh, yeah, pretty close, right? It rounds off pretty close. And then we have taking our x bar, which is 66.8. So now that I've got my E, actually, let me stop before I do any more steps. Okay, so my E is about, why am I not typing? I don't need to do that. Yeah, why am I don't know. E equals 3.1316. 316. I'll leave it there. Okay. And so next I'm going to be doing my X bar, which I'm doing my confidence interval now. So that's going to be, get my little X plus 4 minus E, right? Which is X, which was X bar is 66.8, 66.8 minus 3.316, and also the upper boundary is going to be 66.8 plus 3.316. Come on, guys, give me a break here. Everything has to be so difficult. All right, so there's how I'm going to get my final answer. So I'll do it in here, equals 66.8 minus 3.316 and equals 66.8 plus 3.316, and yep, good job, man. It's really good. And then if I round it to 1 decimal place, just like the others, they match nice and pretty. So it worked out just the same. And that's how you handle that type of problem. So have fun, because there's plenty of them for you to do now because I gave you more homework. Yay! See you later.